A world under a red sun. Would life feel anything like home? If you woke up on an alien world where the sky glows red and the sun never moves, would life still feel like life or something completely different? There are a few thought experiments that cut closer to what we really mean when we talk about finding another home in the universe. We do not just want a rock in space. We want a place where days, weather, oceans, and maybe even biology can actually work. A place that feels, at least in some deep sense, like it could support a living world. But while we often imagine a perfect Earth twin with blue skies and familiar sunshine, reality may be far stranger. The most promising planets do not necessarily look Earth-like at all. In the hunt for alien life, we are learning that the universe may favor worlds that stretch our imagination, worlds where the rules of daily experience, sunrise, sunset, seasons, are rewritten. So what would it mean to call a place like that home? Imagine standing on solid ground while a dim red dwarf star hangs motionless overhead. The sky is not blue, but a deep, ember-like glow. Shadows are long and soft, colors are muted, and the light feels more like late evening than midday. Walk far enough in one direction, and the world darkens into a permanent, frozen night. Walk the other way, and you move into a brighter, warmer zone, but the star still never rises or sets. This is not science fiction. This is the kind of planet our telescopes are now seriously considering. Among these strange candidates, one world has emerged as especially intriguing. LHS 1140b, a super-Earth roughly 1.5 to 2 times the size of our planet, orbiting a cool red dwarf about 48 light-years away in the constellation Cetus. It sits firmly in its star's Goldilocks zone, close enough for warmth, but not so close that it should be instantly scorched. Optimistically speaking, that already makes it a prime target. But the real mystery is what its surface and its potential for life might actually be like. It should be noted that this so-called second Earth is probably nothing like Earth. The planet almost certainly keeps the same face turned to its star, one hemisphere in endless daylight, the other in endless night. This means its surface may be half frozen and half temperate, perhaps with a dark global ocean and a single bright eye of liquid water directly under the star, dimly lit, tidally locked, maybe an ocean world. And that strangeness is exactly why it matters. Because if a world like LHS 1140b can host a stable atmosphere, a working climate, and even primitive ecosystems under a red, unmoving sun, then our definition of habitable has to expand. So let's begin. So it's time to find out the truth. By the end of this video, we will build a vivid, science-grounded picture of what a day, a climate, and even the simplest forms of life on LHS 1140b might actually be like, and ask whether we could ever feel at home there. Why this one planet could rewrite our idea of habitable. In the hunt for alien life, not all planets are created equal. Some are simply beyond our reach, not in distance, but in what we can actually measure. Over the last 3 decades, we have discovered thousands of exoplanets, from scorched hot Jupiters skimming their stars to frozen worlds in the dark. But while that sounds impressive, only a tiny fraction sit in that delicate Goldilocks zone where temperatures allow liquid water and are also close enough, big enough in signal, and quiet enough in their host star for us to seriously probe their atmospheres. This means that, out of a cosmic ocean of worlds, only a handful can currently be tested for signs of habitability at all. For years, the poster children of this search were systems like TRAPPIST-1, 7 Earth-sized planets around a single red dwarf star, all packed in tight, all potential headlines. It should be noted that TRAPPIST-1e, in particular, became the celebrity, a rocky world right in the middle of its habitable zone. But as new data from the James Webb Space Telescope and other instruments arrive, something interesting is happening. Quietly, almost without public fanfare, LHS 1140b is moving to the front of the line. Why this one planet, LHS 1140b, orbits a relatively calm red dwarf about 48 light-years away, and it transits, meaning it passes in front of its star, from our point of view. That geometry is crucial. Every time it crosses, a tiny fraction of starlight filters through any atmosphere it might have, imprinting spectral fingerprints we can read. The planet is larger than Earth, with a stronger gravity and a deeper gravitational well to hold on to gases, and the star is dim and stable enough that its light does not overwhelm the subtle signals we care about. But while this sounds straightforward, the scientific challenge is enormous. We cannot visit, we do not see continents or clouds directly. We see dips in starlight, timing variations in its orbit, and a few faint lines in a spectrum. From that, we must infer mass, radius, density, and whether there is an atmosphere at all. Every conclusion is a puzzle assembled from incomplete pieces, where multiple pictures can fit the same scattered clues. So it's time to find out the truth. What kind of world does the data really point to? For a while, many astronomers thought LHS 1140b might be a mini Neptune, wrapped in a thick hydrogen and helium envelope. That would likely mean high pressures, deep clouds, and little chance for a solid, Earth-like surface where life as we know it could stand. Optimistically speaking, it would still be fascinating, but not the prime second Earth we were hoping for. Then the measurements started to shift. New mass and radius estimates suggested a denser planet, more compatible with a rocky super-Earth, or a water-rich world with a global ocean. Hints of a substantial atmosphere began to emerge, and climate models showed that a tidally locked planet in this orbit could sustain a liquid ocean under a permanent red sun. If that is confirmed, LHS 1140b would become the first potentially habitable exoplanet whose atmosphere and climate we can truly characterize in detail, not just speculate about. So what does that actually look like on the surface? And how close are we to knowing whether this world is oceanic, icy, or something far stranger than either? Meet LHS 1140b, the wrong kind of planet that might be just right. To answer that, we first have to meet the world itself. What kind of planet dares to challenge Earth's status in the hunt for alien life? LHS 1140b orbits a small, cool, red dwarf star about 48 light-years away in the faint constellation Cetus. On cosmic scales, that is practically our neighborhood. This means its light is just close enough and just bright enough for our telescopes to dissect it in detail. The star is only a fraction of the sun's size and brightness, but for LHS 1140b, it is an ever-present red sun hanging in a dim sky. So what sort of planet are we dealing with here? LHS 1140b is what astronomers call a super-Earth. It should be noted that this does not mean a gas giant with rings and dramatic storms. A super-Earth is a world larger and more massive than Earth, but still likely rocky, or perhaps rich in water. LHS 1140b measures about 1.7 times Earth's radius, with several times Earth's mass. Surface gravity would be significantly stronger than on our planet. Every step would feel heavy, as if you were permanently wearing a loaded backpack. That extra mass matters. It helps the planet hold onto a thick atmosphere and possibly a deep global ocean for billions of years. In the hunt for alien life, long-term stability is crucial. A fragile world that quickly loses its air or water has little time for biology to get started. Now consider its orbit. LHS 1140b circles its red dwarf in the star's Goldilocks zone, the region where temperatures could allow liquid water on the surface. But while that sounds wonderfully Earth-like, the geometry is very different. The planet is so close to its star that it almost certainly keeps one face permanently turned toward it. One hemisphere bakes under eternal day, the other is locked in endless night. What does habitable really mean on a world like that? Here is why astronomers are so excited. LHS 1140b passes directly in front of its star from our point of view. Each transit lets starlight filter through any atmosphere, imprinting spectral fingerprints that JWST can read. The host star is also relatively quiet for a red dwarf, flaring less violently than many of its cousins. Optimistically speaking, this calm space weather gives any atmosphere and any potential life a better chance to survive. So it's time to find out the truth. Is LHS 1140b wrapped in a suffocating hydrogen envelope, more mini Neptune than Earth? Is it a dense, rocky super-Earth with scattered seas, or a deep global ocean world, a true Hycean planet? Each option paints a radically different surface and a radically different story for life. Which one matches the data we have so far? The telescopes that turn dots of light into alien worlds. To answer that, we need to ask a different question. How do we turn a distant, invisible world into a place we can actually picture? Right now, LHS 1140b is just a tiny dip in starlight in a telescope's graph. So let's begin with how that dip first appeared. Back in 2017, ground-based telescopes were staring at a faint red dwarf about 48 light-years away. Every time the planet crossed in front of its star, the starlight dimmed by a fraction of a percent. From those repeating shadows, astronomers could work out LHS 1140b's size, its orbit, and that it sat right in the Goldilocks zone. Add in follow-up measurements of the star's wobble, and we got its mass and density. Promising? Yes, but still abstract. A radius, a mass, an orbit period of about 25 days. Not a world you could imagine standing on. In the hunt for alien life, that is only step one. Finding a planet is easy compared to understanding it. So who delivers the real verdict? This is where a different class of instruments steps in. Hubble, Spitzer, and now the James Webb Space Telescope. These are not just discovery machines. They are verdict-delivering telescopes, built to dissect atmospheres and climates using light alone. How do they do that? When a planet, like LHS 1140b, passes in front of its star, a thin ring of atmosphere, if it exists, imprints chemical fingerprints onto the starlight. Different molecules absorb different colors. Hubble could glimpse this in a few nearby systems. Spitzer can measure heat, but JWST combines and amplifies those powers on a scale we have never had before. It should be noted that Webb is essentially a 6.5-meter gold-coated mirror, unfolded in space, feeding ultra-cold infrared detectors, chilled just a few degrees above absolute zero. This means it can sense the faint heat of a super-Earth and tease out the spectral signatures of water vapor, carbon dioxide, methane, or even hydrogen in that tiny atmospheric ring. It can also watch the planet disappear behind the star, measuring the planet's own glow. Now apply that to LHS 1140b. By watching multiple transits and secondary eclipses, JWST can build up a spectrum and ask, is this a light, puffy hydrogen envelope, more mini Neptune than Earth-like, or a heavier, water-rich, or nitrogen-dominated atmosphere that could support oceans? One set of lines in the spectrum, and the mini Neptune dream dies. Another pattern, and suddenly a cool, dense, potentially habitable world emerges. Here is the pattern interrupt. For the first time, the question of habitability here is not just philosophy, it is forensics. Optimistically speaking, the data flowing down now are less like vague hints and more like a courtroom drama. The star is the witness, the spectrum is the testimony, and JWST is the judge. So it's time to find out the truth. When we come back to the surface of LHS 1140b, we will finally know which version of this planet we are allowed to imagine. Is LHS 1140b a dead mini Neptune or a living ocean world? So what kind of world are we actually dealing with here? Right now, LHS 1140b lives in a kind of planetary limbo, suspended between two very different identities. On one side, we have the mini Neptune model, a planet wrapped in a thick, puffy envelope of hydrogen and helium, with no solid surface anywhere a spaceship could land. On the other, we have a dense super-Earth, or water world, with a real interface where rock, ocean, and atmosphere meet. This means our entire picture of its habitability hangs on which of these is true. A mini Neptune sounds exotic, but for life as we know it, it is almost always bad news. In the hunt for alien life, hydrogen-helium worlds are usually the places we quietly cross off the list. Why? Imagine diving into an atmosphere instead of an ocean. As you fall through a mini Neptune skies, pressure and temperature climb relentlessly. There is no stable ground, only deeper layers of compressed gas, then supercritical fluids, then maybe exotic ices or rock far below, hidden under megabar pressures. Chemistry there is wild, but not in a friendly, Earth-like way. Complex molecules are shredded. Liquid water, if it exists at all, occupies strange, transient layers. And there is no long-term, sunlit surface where ecosystems can anchor. It should be noted that such planets might host interesting physics, and perhaps even some speculative forms of life, but they are not the obvious, let's point our telescopes here first, candidates. If LHS 1140b is a classic mini Neptune, it drops almost instantly down the priority ladder. But while that is one possibility, the other is far more exciting. Instead of a gas-wrapped mini Neptune, LHS 1140b could be a Hycean, or ocean world, a dense, water-rich planet with a deep global ocean lying beneath a thick, possibly nitrogen or water vapor-rich atmosphere. Around a dim red dwarf star, that ocean might be partly frozen on the night side, while near the substellar point, a permanent patch of liquid water forms an enormous, dark eye staring at the star. On such a world, temperatures in that Goldilocks zone region could be surprisingly temperate, even under a red twilight sky. Starlight filters through clouds, drives weather, and powers chemistry in the upper ocean. Down below, pressure builds, but liquid water remains, potentially for billions of years. Hydrothermal activity at the seafloor could inject minerals, feeding complex chemistry in a vast, three-dimensional habitat. Optimistically speaking, that is the sort of environment where life might emerge and endure. Not Earth-like in detail, but Earth-like in the key ingredients: liquid water, stable energy sources, and time. So here is the binary question at the heart of this episode. When we finally decode LHS 1140b's atmosphere, will we be staring at a dead mini Neptune we can confidently rule out, or at a living ocean world that jumps straight to the top of our target list? So let's begin to weigh the evidence. In the next sections, we will follow the data, layer by layer, up through the planet's atmosphere. And by the end, we may have to rethink what a habitable world can look like. For now, though, the verdict stays sealed. Who's talking to you, and where this journey is going? For the rest of this journey, we do not want LHS 1140b to feel like an abstract data point. We want it to feel like a place. So before we dive deeper, let's talk about who's guiding you there and how we're going to explore this strange world together. I'm your host, and this is our channel, where we follow the evidence across the galaxy in the hunt for alien life. We take real observations from real telescopes and then carefully push them as far as they can go without falling off the edge into pure fantasy. That balance is especially important here because this planet sits right on the line between maybe and we have to go back and look again. So, let's begin by mapping out the path. First, we will step back from the planet itself and look at its star, LHS 1140, a relatively quiet red dwarf about 48 light-years away. How bright is it? How violent is it? What does its Goldilocks zone actually look like? Because it should be noted that habitability starts with the star. The radiation environment, the stability of the orbit, the age of the system, all of that sets the stage before a single drop of liquid water can exist. Then we will close in on LHS 1140b as a physical world, We will use its mass, radius, and orbit to build an Earth-like mental blueprint. Surface gravity, length of a year, and whether it is tidally locked with one face, forever staring at its star. This means we will confront the old picture of a mini Neptune and compare it to the emerging image of a dense super-Earth, or even a water world. After that, we climb upward into the atmosphere and climate. Does this planet have a thick blanket of gases or a thin, fragile shell? Could there be a global ocean under a dim red sky, or an eyeball world with a single open sea staring at the star? Here we will alternate. One moment, hard numbers from JWST and other observatories. The next, vivid but clearly labeled speculation. You will always know when we are standing on solid data and when we are extrapolating beyond it. Pattern interrupt. Imagine, just for a second, that you wake up there. In the next act, we slow down into detailed day-in-the-life scenarios. What color is the sky? How heavy does your own body feel in the stronger gravity? What chemistry might power simple alien microbes beneath that ocean? And what would their presence do to the atmosphere we observe from 48 light-years away? Finally, we look ahead. So it's time to find out the truth about what future telescopes, JWST, giant ground-based observatories, and missions still on the drawing board could reveal. Optimistically speaking, we might detect the fingerprints of life itself. For the next hour and a half, imagine that you have moved in. This is your world now. Its weather, its oceans, its possible ecosystems. Together, we are about to map it out, piece by piece. How to build an alien climate, the rules before the details. So if this is our new home, what rules does it have to obey? Before we sketch clouds, oceans, and alien ecosystems, we need the basic blueprint of climate itself. In the hunt for alien life, there are three main ingredients that decide whether a planet is truly habitable. First, the star, how much energy it puts out, and in what colors of light. Second, the orbit and rotation, how that energy is spread over the surface, in space, and in time. Third, the atmosphere-surface system, the air, oceans, and rocks that trap, move, and release heat. Change any one of these, and you change the entire story of the world. So let's begin with the star, because everything else depends on it. LHS 1140 is a red dwarf, much smaller and dimmer than the Sun. This means its Goldilocks zone, where liquid water is possible, hugs the star very closely. Planets like LHS 1140b have to orbit in tight, fast loops to get enough light. But while that sounds convenient for observation, it comes with a price. Red dwarfs are tricky neighbors. They emit most of their light in the infrared, so their planets sit under a deep red, almost ember-like glow, rather than bright white daylight. It should be noted that young red dwarfs flare violently, blasting their systems with high-energy radiation that can strip atmospheres and sterilize surfaces. And because the habitable zone is so close in, gravity tends to grab onto a planet's rotation and slow it down until one side always faces the star. This is tidal locking. One hemisphere in endless day, the other in eternal night. What does that do to climate? Imagine the day side under a constant red sun, absorbing heat without respite, while the night side radiates its warmth away into space. Without something to move energy around, one side could boil, the other freeze solid. No global ocean, no stable environment, no comfort zone for life. This means the atmosphere and any oceans become the planet's life support system. A thick, mobile atmosphere can transport heat from day to night, smoothing out extremes and allowing a wide ring of temperate conditions around the terminator, the line between light and dark. A thin atmosphere, or none at all, leaves the world split, scorched rock facing the star, airless ice in the dark. We have powerful examples right here in our own system. Earth, with its modest nitrogen-oxygen atmosphere, holds liquid water over most of its surface and keeps temperatures in a relatively narrow band. Venus, with a crushing blanket of carbon dioxide, over 90 times thicker than Earth's, is a runaway greenhouse, hot enough to melt lead, despite receiving only slightly more starlight than we do. Same basic star, very different climate outcomes. So it's time to find out the truth about LHS 1140b. To know whether it can host oceans, clouds, and maybe even biology, we first have to judge the star it orbits. How violent was its youth? How calm is it now? In the next section, we will dissect LHS 1140 itself and see just how gentle or how hostile this little red sun really is. The little red sun of LHS 1140. Friend or foe to life? So let's begin with a little red sun at the heart of this story. LHS 1140's star is not impressive by human standards. It is an M dwarf, a small, cool, red dwarf with only a fraction of the sun's mass and radius. Picture a sphere barely larger than Jupiter, yet far denser, glowing a deep, ember-like red. It puts out far less total energy than our sun, so its Goldilocks zone is pulled in close, like planets huddling around a dying campfire. In the hunt for alien life, that actually sounds promising at first. Red dwarfs are the most common type of star in the galaxy. Most of the stars in our local neighborhood are red dwarfs, quietly burning hydrogen at a miserly rate. This means they can live not just for billions, but potentially trillions of years. If life needs time and stability, what could be better than a star that barely changes over the entire visible history of the universe? But while their longevity is appealing, their neighborhoods are strange. Because a red dwarf is so dim, any habitable planet has to orbit very close in to receive Earth-like warmth. LHS 1140b, for example, sits in a tight orbit of just a few weeks. At that distance, gravity tends to tidally lock the planet, freezing one hemisphere into eternal night while the other stares forever at the star. Can an atmosphere really shuffle heat around fast enough to keep such a world truly habitable? Or does it end up with a scorched eye and a frozen dark side? It should be noted that proximity brings another problem: violence. Young red dwarfs are notorious for intense stellar flares and high-energy radiation. They can unleash blasts of X-rays and ultraviolet light that dwarf anything our sun throws at Earth. Over hundreds of millions of years, that kind of punishment can strip away atmospheres and sterilize exposed surfaces, especially on small, low-gravity planets. So how does the star of LHS 1140 compare to a more infamous cousin like Proxima Centauri? Proxima is a textbook example of an active red dwarf, flaring frequently, with X-ray outbursts that slam its planet Proxima b. Any atmosphere there would have to endure a relentless sandblasting for billions of years. LHS 1140's star appears quieter and less flare-happy in the data we have so far, but even a calmer red dwarf still emits more high-energy radiation relative to its total light than the sun does. This means LHS 1140b's atmosphere, if it exists, has been on the defensive since day one. Optimistically speaking, a thick, resilient atmosphere and maybe a magnetic field could survive this onslaught. Yet on paper, a close-in planet around a red dwarf should struggle to hang on to a cozy, life-friendly envelope of air. So why are astronomers so excited about LHS 1140b anyway? And what has JWST actually seen above that alien horizon? Why this red dwarf might be surprisingly gentle? To answer that, we have to look not just at the planet, but at the star itself. Is LHS 1140 one of those angry, atmosphere-stripping red dwarfs, or something much rarer? Evaluating a star system for compatibility with life is tricky. A huge part of the story is how violently the star behaves over billions of years. Most M-dwarf stars start out hyperactive, blasting their planets with flares and X-rays that can tear an atmosphere away. In the hunt for alien life, that has made many astronomers deeply skeptical of red dwarfs in general. But while the stereotype is small, dim, and dangerous, LHS 1140 seems to be the opposite. Observations from ground-based telescopes and X-ray observatories show that this star is old and relatively quiet. Its rotation period is long, a classic sign of stellar aging and spin down. It should be noted that younger red dwarfs spin quickly and flare often. Older ones slow down and calm down. So how calm are we talking about? When astronomers monitor LHS 1140 over many nights, they see very few large flares in an entire year, whereas notorious flare stars of similar type can throw off powerful eruptions weekly or even daily. In X-rays, LHS 1140's luminosity is measured to be an order of magnitude or more below those wild cousins. This means the high-energy radiation that drives atmospheric escape is dramatically reduced. Pattern interrupt. Imagine replacing its star with Proxima Centauri for a moment. Proxima's frequent, violent flares likely erode any fragile envelope of air on nearby planets. Now swap back to LHS 1140. Suddenly, LHS 1140b's thick, gravity-clinging atmosphere does not feel so doomed. For LHS 1140b, this quiet behavior is everything. A calmer star means the planet's upper atmosphere is less superheated, so gas molecules are less likely to reach escape velocity and leak into space. Instead of being stripped to a bare, airless rock, a super-Earth in the Goldilocks zone can plausibly hang on to a dense atmosphere, maybe even support a stable ocean at the surface over billions of years. Optimistically speaking, that long-term stability is exactly what complex chemistry, climate feedbacks, and perhaps even biology would need. And here, red dwarfs reveal their hidden advantage. While our sun will burn for about 10 billion years in total, a low-mass red dwarf like LHS 1140 can shine steadily for hundreds of billions, even trillions of years. So it's time to find out the truth about these so-called hostile stars. If you place a relatively gentle red dwarf in the right regime of age and activity, it becomes less a cosmic flamethrower and more a dim but steady campfire. For a planet like LHS 1140b, locked in close orbit, that could be the perfect backdrop for an alien biosphere to slowly emerge. So let's begin to imagine what that world might actually feel like from the surface, and what kind of sky you would see if you stood under that quiet red sun. From flicker to planet, how we first found LHS 1140b. To picture that sky properly, we have to ask a simple question. How did we even find this distant world in the first place? Because from our vantage point, LHS 1140b began as nothing more than a tiny, rhythmic flicker in the light of a faint red dwarf. In the hunt for alien life, that flicker is everything. Around 2014 to 2017, ground-based surveys were staring at thousands of cool, nearby stars, taking brightness measurements night after night. LHS 1140, a dim red dwarf about 48 light-years away in Cetus, looked almost boring at first. But then astronomers noticed it. Every 24.7 days or so, the star's light dipped by less than 1%, and then returned to normal. Could a planet be crossing the star's face? This is transit photometry in action. Imagine the star as a distant light bulb and the planet as a tiny moth drifting across it. For a few hours, the moth blocks a sliver of that light. The depth of the dip tells us how big the planet's silhouette is. The time between dips tells us its orbit. It should be noted that for LHS 1140b, that dimming was incredibly subtle, especially through Earth's turbulent atmosphere. So astronomers brought in more precise instruments. Robotic telescopes like M-Earth watch the star from the ground, while space-based observatories such as Spitzer refined the timing and shape of each transit from above the atmosphere. This means we could measure the radius of LHS 1140b to within a few percent and pin down its orbital period, confirming that it sits squarely in the star's Goldilocks zone. But a radius alone does not tell us what kind of planet this is. Is it a puffed-up mini Neptune or a compact, rocky super-Earth? To answer that, astronomers turn to a second technique, radial velocity. As the planet orbits, its gravity tugs on the star, making the star wobble slightly toward and away from us. Sensitive spectrographs, such as HARPS, measured tiny shifts in the star's spectrum, just a few meters per second, like walking speed. From that wobble, they derived the planet's mass. Now we had both mass and radius, and therefore density. LHS 1140b turned out to be relatively dense, heavier than an Earth-like planet of the same size would be, and far too compact to be dominated by a thick hydrogen-helium envelope. Optimistically speaking, that ruled out the simplest mini-Neptune scenario and pointed instead toward a mostly rocky world, perhaps with significant water. So it's time to find out the truth. What does a dense, close-in planet in the habitable zone of a quiet red dwarf actually look like up close? And could that faint flicker really be the signpost to an ocean world? The next step is to stop just weighing and timing this world and to start probing its atmosphere itself. When the numbers don't agree, mini Neptune or super Earth? We've weighed the planet, we've timed its orbit, but what do those numbers actually tell us about what LHS 1140b is? To answer that, we have to slow down and look at how astronomers turn tiny dips in starlight and subtle stellar wobbles into a story about an alien world. When the planet passes in front of its red dwarf star, the star's light drops by a precise fraction. That tells us how big the planet's disk is, and therefore its radius. Then, as the planet tugs on the star in its orbit, the star moves back and forth. Measuring that wobble gives us the planet's mass. Put those together, and we get density. Mass divided by volume. This sounds straightforward, but here's the catch. The same density can be produced by very different internal structures. In the hunt for alien life, that ambiguity is a serious problem. For LHS 1140b, the early data painted a confusing picture. With a radius about 1.7 times Earth's and several times Earth's mass, its bulk density landed in an in-between zone. It could be a rocky super-Earth, perhaps with a lot of water mixed in. Or it could be something quite different, a small, dense core wrapped in a thick, puffy shell of hydrogen and helium. In exoplanet language, that second option is a mini Neptune. Not a gas giant like Jupiter, but a scaled-down version with a deep envelope of light gases sitting on top of any solid surface. It should be noted that many planets with similar size and mass in other systems do turn out to have these extended hydrogen atmospheres. So, statistically, the mini Neptune interpretation for LHS 1140b was initially very plausible. But while a mini Neptune might be fascinating, it is almost certainly not habitable at the surface. A thick hydrogen blanket would trap heat, crush any ocean beneath enormous pressure, and blur the boundary between atmosphere and interior. If you tried to stand there, where would the surface even be? By contrast, the same density could also be matched by a denser, rock and water-rich planet with a thinner, heavier atmosphere, more like a supersized, colder version of Earth. This means that on paper, LHS 1140b could either be a high-pressure, steamy mini Neptune or a potentially oceanic super-Earth sitting in the Goldilocks zone. One scenario almost rules out surface life. The other makes it one of the most exciting Earth-like candidates in the local universe. How can the same basic measurements describe such radically different realities? Optimistically speaking, the answer is simple. We are missing a critical piece. Mass and radius tell us the bulk story, but not the outer layers that matter most for habitability. So it's time to find out the truth by looking directly at the planet's atmosphere. Without that, we are stuck between two very different worlds occupying the same set of numbers, and only a telescope like JWST can break the tie. Before we imagine oceans, a quick reality check. But before we dive into alien oceans and twilight coastlines, we need to pause. What do we actually know about LHS 1140b, and what are we carefully imagining? In the hunt for alien life, it is very tempting to treat every artist's impression as a photograph. Yet we have never seen this planet as a disk in a telescope. No continents, no waves, no clouds. What we really have are light curves, spectra, and physics. This means every view of LHS 1140b is a reconstruction built from how the star's light dips when the planet passes in front, and how that light is filtered through whatever atmosphere might surround it. So let's begin with the firm ground. We know LHS 1140b orbits a small red dwarf about 48 light-years away in the constellation Cetus. We have measured its orbital period precisely. It circles its star in just under 25 Earth days. Transit depths and radial velocity data give us a radius around 1.7 times Earth's and several times Earth's mass. From that, we infer a high density compatible with a rocky super-Earth rather than a puffy gas mini Neptune. We also know the star's luminosity and temperature well enough to say the planet sits in the Goldilocks zone, where liquid water on the surface is, in principle, possible. However, while those numbers are solid, the picture beyond them is much blurrier. What is the exact composition of its atmosphere, if it has one at all? Is it dominated by nitrogen and water vapor, by CO2, or by something more exotic? How thick is that atmosphere? And how many clouds does it carry on its day side versus its night side? We do not yet know the depth of any ocean, the layout of any continents, or even whether there is exposed rock at the surface. The internal structure, tectonic activity, and the presence or absence of a magnetic field that could shield life from stellar radiation all remain open questions. Pattern interrupt. What if everything we say next turns out to be wrong? It should be noted that we are capturing this planet at a very early stage of exploration. JWST has only just begun to probe its atmosphere. Future observations with JWST, the extremely large telescope, or even more advanced space telescopes, could tighten the error bars, reveal unexpected molecules, or overturn entire scenarios we currently consider plausible. Optimistically speaking, that is a feature, not a bug, of frontier science. So it's time to find out the truth about how we will proceed. From here on, we will clearly separate two modes. When we talk about things like the orbit, size, mass, and stellar radiation, we are anchored in observations and well-tested models. When we start describing an eyeball world with a central ocean, red skies, or potential ecosystems, we are stepping into informed thought experiments. Both are essential if we want to understand what life on LHS 1140b might feel like. But we should always know which world we are standing in, the measured one or the imagined one. Big picture habitability. Does this system even stand a chance? So if that is the line between what we know and what we imagine, where does LHS 1140b actually sit in the big picture of habitable worlds? We have found thousands of exoplanets scattered all across the Milky Way. But while the catalog is huge, most of those worlds are terrible candidates for life as we know it. They are blistering hot Jupiters grazing their stars, frozen giants in the dark, or small worlds so distant and faint that we can barely measure more than a whisper of their existence. LHS 1140b is different. In the hunt for alien life, it should be noted that we are constantly searching for a rare overlap of three things: a planet that is roughly Earth-like in size, that sits in the Goldilocks zone of its star, and that we can actually study in detail. This means it has to transit, be close enough to us, and orbit a star that is not wildly hostile. LHS 1140b quietly checks all three boxes. So let's begin at the system level. As far as we know today, LHS 1140 has one confirmed planet. No tightly packed chain of 7 worlds like TRAPPIST-1. No sprawling miniature solar system. Just this one super-Earth, about 1.7 times Earth's radius, circling a relatively quiet red dwarf roughly 48 light-years away. Yet that single world sits right in the middle of the star's habitable zone, where liquid water on the surface is at least physically possible. That location does come with a catch. To stay warm around such a cool, dim star, LHS 1140b has to orbit close in, completing a year in only about 25 days. A compact orbit like this is a double-edged sword. On one side, it is perfect for us. Frequent transits, deep signals, and rich data for telescopes like JWST to probe the atmosphere. On the other side, it almost certainly means tidal locking, with one hemisphere facing the star forever. Tidal locking can be brutal. One side risks constant irradiation, the other, endless night. Without a substantial atmosphere or ocean to move heat around, you end up with a world of extremes: a baked day side, a frozen night side, and a narrow ring of survival in between. But if LHS 1140b really does have a thick atmosphere and maybe a deep ocean, those same compact conditions could produce a stable, long-lived climate instead of a frozen wasteland. Optimistically speaking, this entire system looks unusually promising. We have a red dwarf that seems comparatively calm, a planet squarely in the right temperature range, and transit signals strong enough for us to start teasing out atmospheric fingerprints. Among the thousands of worlds we have found, LHS 1140b rises to the top tier of places where a truly habitable surface is not just possible, but testable. So it's time to find out the truth. Given everything we have seen so far, is LHS 1140b just another interesting rock with a clever nickname? Or is this the first alien world where we can seriously talk about real weather systems, real oceans, and maybe even real life? To answer that, we have to step onto the planet itself, and what we find there might be stranger than any Earth twin. Gravity, size, and the feel of standing on LHS 1140b. So if we could stand on LHS 1140b, what would it actually feel like to be there? This is where the numbers stop being abstract and start pressing down on your shoulders. LHS 1140b is not an Earth twin. It should be noted that this planet is bigger in almost every sense. Its radius is around 1.7 times that of Earth, and the mass estimates come in at several times Earth's mass. Put those together, and most models land on a surface gravity somewhere around 1.5 to almost twice Earth's. This means that if you weigh 70 kilograms on Earth, the ground here effectively pulls on you as if you were 100 to 130 kilograms. What does that do to your body? Every step would feel like walking with a very heavy backpack you can never take off. Your leg muscles would burn after just a short walk. Try to jump, and you rise only half as high, maybe less, before slamming back down faster than you expect. Even your own chest would feel heavier. Your heart and lungs would have to work harder to push blood and air around. In the hunt for alien life, we often imagine familiar, comfortable worlds. But LHS 1140b immediately reminds us that habitable does not mean easy. Is it survivable? Optimistically speaking, yes. at least for adapted humans. Astronauts train in centrifuges at 2G for short periods. Fighter pilots endure even higher loads. The difference here is that you never get a break. Children born on this world, or on a long-term base, might grow shorter and stockier, with powerful legs and dense bones, shaped by this higher gravity, the way deep-sea creatures are shaped by pressure. But that extra gravity does something very important for the planet itself. A more massive, compact world can hold on to gases far more effectively. Nitrogen, carbon dioxide, water vapor, all the ingredients we associate with a stable, protective atmosphere are harder to lose to space. Around a red dwarf star that can be active, that matters. A strong gravitational grip combined with a magnetic field could mean that LHS 1140b has kept a thick, insulating atmosphere for billions of years. That, in turn, reshapes the surface. Under stronger gravity, mountains cannot soar as high before their own weight makes them collapse and spread out. Instead of sharp, jagged peaks like the Himalayas, we might see broad, squat ranges, more like oversized plateaus. Oceans could be deeper and more globally connected, their waters pressed down into the crust with enormous force, yet still liquid in the Goldilocks zone around this dim star. And the air itself? Denser, heavier, able to move heat efficiently from the blazing day side toward the frozen night. Imagine standing at the substellar eye of this eyeball world, feeling a constant, powerful wind as the atmosphere works overtime to even out extremes. So let's begin to picture not just a point in a graph, but a place where weather, water, and weight all conspire to create an alien, yet potentially habitable environment. In the next section, we will see what that means for oceans, ice, and the thin red light that powers any possible life there. So it's time to find out the truth of what those seas and skies might really look like. Locked in twilight, orbit, rotation, and the eyeball world. To understand those seas and skies, we first have to understand how this planet moves. LHS 1140b does not drift lazily around its star the way Earth does. It races around its red dwarf in just a few weeks, hugging close in the habitable Goldilocks zone where liquid water is possible. This tight orbit means the star's gravity has had billions of years to twist the planet's rotation into a very specific configuration. This means LHS 1140b is almost certainly tidally locked. So what does that actually look like? On a tidally locked world, one hemisphere always faces the star, eternal day. The other hemisphere always faces away, eternal night. There is no sunrise, no sunset, no spinning cycle of morning and evening like we experience on Earth. Instead, the sun, a dim red disk, simply hangs in one spot in the sky, forever. It should be noted that this creates three very different realms on a single planet. Under the substellar point, where the star sits directly overhead, the surface receives constant, unblinking radiation. On the far side, the night hemisphere is locked in deep cold, lit only by starlight from the rest of the universe. And between them lies a narrow ring, the terminator zone, where the star forever hovers on the horizon, locked in an endless red sunset. From space, climate models suggest this could turn LHS 1140b into an eyeball Earth. In the hunt for alien life, that phrase describes a world with a bright, potentially ice-free ocean or warm patch at the substellar point, surrounded by a vast, frozen night side. The central liquid region would form the pupil, while concentric rings of ice and cloud trace out the iris and white of the eye. One glance, and the whole climate pattern is written on the surface. But while the geometry is simple, the atmosphere's response is not. Intense heating at the substellar point would drive powerful updrafts, lofting warm air high above the surface. High-altitude winds would then race toward the night side, where that air cools, sinks, and surges back along the surface. This global conveyor belt of air and potentially water vapor could blur the line between blazing day and frozen dark, perhaps carving out a wide, habitable band of moderate temperatures. Optimistically speaking, that twilight ring might be the most comfortable place for Earth-like life. Imagine standing there, the red dwarf star locked on the horizon, the sky split between glowing ember and deep indigo, winds constantly whispering past as the planet tries to balance its heat. So if you had to choose, where would you live on LHS 1140b? Beneath the blinding red noon, in the silent ice of the dark side, or in the endless sunset in between? And what would each of those alien neighborhoods really feel like on your skin, in your lungs, under your feet? So it's time to find out the truth in the next part. What JWST is whispering about LHS 1140b's atmosphere? To answer that, we have to listen to what the light itself is telling us. Because if you want to know what it would feel like to breathe on LHS 1140b, you first have to find out whether there is anything to breathe at all. The main tool here is something called transmission spectroscopy. When the planet passes in front of its red dwarf star, a tiny fraction of the starlight filters through the planet's atmospheric limb, that thin ring around the edge. Different gases in that atmosphere absorb very specific colors of light. By spreading the starlight into a spectrum and measuring which wavelengths go missing, JWST can, in principle, read the chemical fingerprint of this distant world. It sounds almost magical, but the reality is subtle. LHS 1140b is only about 1.7 times Earth's radius, and its atmosphere, if it has one, is not dramatically inflated. That means the signal is incredibly small. In the hunt for alien life, this is where we are really pushing the limits of what our telescopes can do. Each transit adds a few more photons to the puzzle, and slowly, a picture is emerging. Early on, one popular idea was that LHS 1140b might be a mini Neptune, a rocky or icy core wrapped in a very puffy hydrogen-helium envelope. If that were true, the atmosphere would be large and extended, and hydrogen's strong spectral features would carve deep, obvious notches into the spectrum. But while the data are still noisy, that dramatic, hydrogen-rich signature is simply not there. This means the planet almost certainly does not have a thick, primordial hydrogen-helium shroud. Instead, the observations fit better with a denser, more compact atmosphere, something dominated by heavier molecules like nitrogen, carbon dioxide, or water vapor. It should be noted that this is exactly the kind of shift we saw with TRAPPIST-1e, where JWST quietly ruled out the fluffiest atmospheres first. Now here is the pattern interrupt. There may be hints, just hints, of water vapor in the infrared. Some analyses report slight features where water should absorb, especially in the wavelengths where JWST is most sensitive. Are we seeing the breath of a global ocean or just statistical noise? At this stage, they are not robust detections. Optimistically speaking, the signals are intriguing, but astronomers are being very careful not to overclaim. Why is water in the infrared such a big deal? Because water has strong, distinctive bands that are hard to mimic with other common gases. If we confirm those features, alongside a lack of hydrogen, we are looking at a heavier atmosphere with substantial surface pressure. That kind of blanket can keep temperatures in the Goldilocks zone for liquid water seas, especially on a tidally locked, eyeball-style planet. A nitrogen-water CO2 mix could mean a cool, deep ocean under a cloudy red sky. Add a bit more CO2, and the greenhouse warms the world into steamy, stormy conditions. Add methane, and you change the infrared balance again. So it's time to find out the truth. Even with JWST, tiny shifts in composition can spell the difference between a temperate ocean world and a saturated, sauna-like hothouse. And we still have not asked the most tempting question. If such an atmosphere really exists, what traces of life might it leave behind in that spectrum? Hycean, rocky, or something in between. So if LHS 1140b's spectrum might hide traces of life, what kind of world are we actually looking at? Are we dealing with a deep, endless ocean under a hydrogen sky, or a scaled-up rocky Earth with seas and continents under a red sun? So let's begin with the Hycean idea. A Hycean world is a planet wrapped in a global ocean, hundreds of kilometers deep, with a hydrogen-rich atmosphere that is thick but not extremely puffy, like a classic mini-Neptune. This means there is no solid ground to stand on, just layer after layer of high-pressure water merging into exotic ice at depth. Around a dim red dwarf star, that hydrogen blanket can trap heat very efficiently, keeping the surface of the ocean in a temperate range even when the incoming starlight is weak. In the hunt for alien life, that combination of water and steady temperatures is extremely attractive. But while Hycean planets sound promising, they are very different from the Earth-like template we know. On such a world, the ocean may be so deep that the rocky seafloor is buried under crushing pressures. No plate tectonics at the surface, no continents, no shallow coastal zones. Life, if it appears, might be restricted to the upper ocean, feeding on faint red light from the star and on chemistry leaking up from below. Could complex ecosystems evolve in that endless water column without land or shallow reefs to diversify habitats? We do not yet know. Now contrast that with a rocky super-Earth scenario. In this picture, LHS 1140b has a solid surface, maybe a few times Earth's mass, with gravity strong enough to hold a dense, nitrogen-dominated atmosphere mixed with CO2, water vapor, and possibly oxygen. It should be noted that even a modest ocean on such a planet could be tens of kilometers deep, but still allow continents or island chains to break the surface. Under a red dwarf sun, skies would glow dim crimson. Clouds would reflect that light over the dayside, and an eyeball pattern of ice and water could carve the surface into distinct climate zones. Optimistically speaking, that is a recipe for diverse, Earth-like ecosystems. Current data place LHS 1140b's density in an intriguing middle ground, too dense to be a classic gas-rich mini-Neptune, yet not so dense that it must be a dry iron rock ball. This means both a water-rich Hycean and a more conventional, rocky super-Earth remain on the table. JWST's constraints on a huge, puffy atmosphere favor a compact envelope instead. But within that envelope, many detailed combinations of rock, water, and gas are still allowed. So which biosphere would be more likely here? Deep ocean microbes drifting through a twilight sea? Or surface forests and alien shorelines under a red sun? And if we can answer that for LHS 1140b, what does it tell us about the most common kind of habitable world in the universe? Climate under a red sun. Temperatures, winds, and weather. So if LHS 1140b really is one of the most common kinds of habitable worlds in the universe, what does its weather actually feel like? To answer that, we need to imagine the climate under a small, dim, red dwarf sun that never moves in the sky. Because the planet is almost certainly tidally locked, one hemisphere always faces the star. The substellar point, the spot directly under that red sun, acts like a permanent tropics. This means it receives the most energy, all day, every day. If LHS 1140b has a thick, heat-redistributing atmosphere, simple energy balance arguments suggest that even though it orbits in the Goldilocks zone, the substellar region might sit somewhere between 0 and 20 degrees Celsius, mild by Earth standards, but under a crimson sky. Move away from that bright eye, and the picture changes quickly. Without an atmosphere, the night side would plunge to hundreds of degrees below freezing. But with dense air and perhaps a deep ocean, heat is constantly transported into the darkness. Optimistically speaking, the global average might hover just below freezing, with the coldest nightside basins dropping to maybe -80 or -100 degrees, while high plateaus of air above them remain warmer. Not a frozen airless tomb, but a frigid, slow-breathing hemisphere. The real sweet spot could be the terminator, the ring around the planet where day meets night. Here, the energy from the star is weaker than at the substellar point, but still steady. If the substellar ocean is near the melting point of water, then along this endless twilight band, temperatures could sit between -10 and +10 degrees. It should be noted that on a super-Earth with stronger gravity, a thick atmosphere can smooth out extremes even more, stretching that habitable ring wider than our first estimates. But while the temperatures provide the backdrop, the true drama comes from the winds. Day-night contrasts drive powerful flows as warm air rises under the red sun and races toward the dark hemisphere, cools, sinks, and rushes back along the surface. The whole planet becomes a global heat engine. We expect roaring jet streams circling the terminator, with storm systems locked into near-permanent tracks. Imagine something like Earth's equatorial Hadley cells, but scaled up and welded in place, endlessly pumping energy into the night. Clouds are the wild card. Over the substellar point, intense heating could build a thick, bright cloud deck that reflects much of the incoming starlight. This means the surface beneath might be cooler and more stable than you would think, perhaps a calm, gray-lit ocean rather than a boiling cauldron. Along the terminator, thinner and broken clouds might let more red light through, creating a band of soft, Earth-like illumination where liquid water, moderate temperatures, and dynamic weather coexist. In the hunt for alien life, that twilight ring may be the most promising real estate on the planet. So it's time to find out the truth. If you could stand there or dive beneath those waves, what would you actually see, hear, and feel on LHS 1140b? A day in eternal day, standing at the substellar point. So let's begin right at the most extreme address on LHS 1140b, the substellar point. What does it feel like to stand where the star never moves, where it is always, forever, directly overhead? Look up, and the first thing you notice is how wrong the sky feels to Earth-trained eyes. The host star is a dim, swollen ember, pinned in place, a deep red disk that never arcs, never rises, never sets. Its light is weaker in the visible, but rich in infrared. So the whole landscape is washed in crimson and blood orange tones. It should be noted that climate models suggest thick, bright clouds may gather right under that fixed sun, spreading like a luminous shield that softens the glare. Instead of a harsh spotlight, you get a glowing red ceiling, bright yet strangely muted, as if the world is lit from inside a storm lamp. What about temperature? Optimistically speaking, if LHS 1140b has a dense atmosphere and a stable ocean, the substellar region might be surprisingly comfortable. Not freezing, not boiling, but somewhere in a broad, Earth-like range. Perhaps 0 to 30 degrees Celsius. Humid, certainly. The air would feel heavy on your skin, pressing gently against you with higher pressure than on Earth. Each breath would be thick, almost velvety, and you might notice your lungs working just a little harder. This means the environment is not instantly lethal, but it is undeniably alien. Now picture the ground beneath your feet. In the Hycean scenario, you are standing on a floating platform above a vast, dark ocean. The water looks nearly black under the red star, with slow, deliberate waves that catch faint highlights like molten metal. There is no glittering blue. Instead, reflections are maroon and copper, fading quickly into shadow. Low, dense clouds drift overhead, their undersides glowing red-white, their tops vanishing into a perpetual mist. In the rocky super-Earth scenario, you stand on a plateau of basalt and iron-rich rock, stained dark and wet by constant condensation. Thin veils of fog cling to the ground, sliding past jagged outcrops, as if the whole planet is exhaling. Could life adapt here? In the hunt for alien life, this is where things become truly fascinating. Under a red dwarf, eyes might evolve to be most sensitive to deep reds and near infrared, with pupils that open wide in the dim visible light, yet still see clearly in the star's unseen glow. Plants, or their alien equivalents, would likely appear almost black, packed with pigments that harvest every stray photon. You stand in a world of dark foliage under a fixed red noon, where shadows barely move and circadian rhythms must be written into chemistry rather than sunrise. Listen for a moment. There is a constant wind flowing from the frigid night side toward this warm eye of the planet, a low, endless roar in the background. Surface gravity, stronger than Earth's, pulls you down with undeniable weight. Every step feels deliberate, your muscles always aware of the extra burden. And then the strangest realization hits you. At this exact spot, there is no dawn to wait for, no evening to mark the day's end. On LHS 1140b, at the substellar point, time passes, but the sky never changes. So it's time to find out the truth. What happens when we leave this eternal noon and travel toward the dark? Life on the edge, the habitable ring of eternal sunset. As we walk away from that frozen noon and toward the darkness, something strange happens. The sky finally begins to move. Not quickly, not like a sunrise on Earth, but as a slow, eternal transition from blinding day into endless dusk. On a tidally locked planet like LHS 1140b, there is a narrow band encircling the world where the star never rises higher or sinks lower. It just hangs there, pinned to the horizon, casting long, distorted shadows across ice, rock, or ocean. This is the Terminator, a ring of permanent sunset where every direction feels like late evening and the landscape lives in a world of soft, red twilight. Temperatures here would be neither scorching nor frozen, but somewhere in between. Why does this thin ring matter so much in the hunt for alien life? Climate models of tidally locked worlds repeatedly point to this zone as the sweet spot. On the day side, intense heating drives air upward. On the night side, cold, dense air sinks. Between them, at the twilight band, the circulation balances out. This means more moderate temperatures, winds that are strong but not planet-scouring, and, crucially, the potential for liquid water to pool in lakes, seas, or even a continuous ocean shore. Optimistically speaking, this could be LHS 1140b's true Goldilocks zone. So what kind of ecosystems might claim this ring of eternal sunset? Imagine hardy, low-growing plant analogs clinging to the ground, evolved under a dim, reddish glow. Their pigments might be tuned not to blue light, like many plants on Earth, but to the deep red and near-infrared light of a cool, red dwarf star. Instead of tall forests, we might see sprawling mats, thick carpets, and squat, wind-hugging stalks, all arranged to catch that slanting light that never shifts overhead. Animals or microbes here might migrate, not north and south with seasons, but around the planet itself. If the most habitable temperatures form a moving band shaped by the atmosphere and the ocean, life could slowly drift or swim along it, always chasing its preferred conditions. It should be noted that on a world with higher gravity than Earth, creatures might be compact and sturdy, built low to the ground, conserving energy with every step. And what about us? Human settlers might build a chain of cities along this twilight ring, each one facing the star's red disk on the horizon. The bright day side could be covered with vast solar farms, feeding power back to the habitable band, while the deep night side hosts cooling facilities, data centers, and long-term storage buried in eternal darkness. High-speed rail or vacuum tube lines could circle the planet, tying this ring of light together into a continuous civilization. So it's time to find out the truth. If life really thrives in this eternal sunset under a dim red star, what would its chemistry look like? And from nearly 50 light years away, would we even recognize its fingerprints in the atmosphere? Or could an entire biosphere hide in plain sight? Into the dark, the frozen night side, and hidden oceans. But what if the most promising habitats on LHS 1140b are not in that glowing ring of twilight at all? What if in the hunt for alien life, the real story is unfolding on the side of the planet we never see lit? Step with us across the Terminator, over the last line of dim red, and into the deep night hemisphere. Here, the red dwarf star never rises. The sky is a vault of sharp, unblinking stars, far denser than most of us have ever seen, because there is no dawn to wash them out. The landscape below is a continent of shadow, broken only by slow curtains of aurora, where the planet's magnetic field funnels charged particles into the upper atmosphere, and by a faint, ghostly glow, sunlight scattered through high clouds on the day side and reflected back across the curve of the world. At first glance, you might expect this hemisphere to be a dead, airless freezer. After all, with no direct starlight, why would anything here be above absolute zero? But while the surface never sees the star, the atmosphere and oceans do. Winds carry heat from the substellar ocean into the darkness, and powerful currents can drag relatively warm water under the nightside ice. This means that, instead of a solid block of frozen rock, simulations suggest a thick shell of ice, perhaps kilometers deep, floating on a global ocean that could remain liquid far below. It should be noted that we have analogs for this right here in our own system. Europa, around Jupiter, and Enceladus, around Saturn, both orbit far outside the classic Goldilocks zone, yet they hide vast subsurface oceans beneath their ice. There, tidal flexing from their giant planets stirs their interiors and keeps water liquid. On LHS 1140b, tidal heating from its tight orbit and strong gravity, plus the constant shuttling of heat from the day side, could carve out similar dark oceans under the frozen nightcap, even at the very anti-stellar point. So let's begin to imagine what life would do with that. Without sunlight, photosynthesis fails, but chemistry does not. Hydrothermal vents on the ocean floor could pump out minerals and energy, just as they do on Earth's mid-ocean ridges. Chemoautotrophic microbes might feed on gradients of hydrogen, methane, and sulfur, building entire ecosystems without ever seeing the star. Above them, drifting in the black water, more complex organisms could evolve to rely on something else, light made by life itself. Bioluminescence would not be a rare party trick. It could be the main illumination system of this hidden ocean. Imagine slow-moving grazers tracing glowing paths through the dark, predators using flashes and patterns as lures, and vast clouds of plankton creating dim, shifting constellations beneath the ice. From above, the frozen nightside might look dead. From below, it could resemble an inverted, living sky. Here is the pattern interrupt. While our telescopes obsess over the atmosphere above the bright hemisphere, searching for oxygen or methane in starlight, the real cradle of life on this planet might be sealed away under kilometers of ice, perfectly shielded from flares and radiation from the red dwarf. Optimistically speaking, that would make LHS 1140b not just an Earth-like world, but a double world, a bright, marginally habitable surface, and a dark, stable ocean biosphere we can barely touch with current data. So it's time to find out the truth. If such hidden oceans do exist, could their chemistry ever leak out into the atmosphere in a way we can detect from nearly 50 light years away? Or will the next section show that we need entirely new strategies to read the fingerprints of a civilization or biosphere that never sees its own star? Breathing the air. Pressure, composition, and human survivability. If that hidden ocean is really there, what would it actually feel like to stand above it and breathe? Could we, in any meaningful sense, share this world with whatever might live there? So let's begin with the weight of the air itself. LHS 1140b is a super-Earth, with gravity probably around 1.5 to 1.7 times Earth's. In the hunt for alien life, that extra pull matters. A thick, long-lived atmosphere is easier to hold onto, so surface pressures of 2, 3, even 5 times Earth's are entirely plausible. Imagine walking through air that feels like you are perpetually at the bottom of a deep valley, or under several meters of water, except you are dry. Every breath would feel dense and resistant, like inhaling through a snorkel filled with heavy fog. But pressure is only half the story. What is that air actually made of? One realistic option is a nitrogen-dominated atmosphere, like Earth's, with a healthy dose of carbon dioxide and water vapor. This means greenhouse warming, strong enough to keep the substellar ocean liquid. But chemically, nitrogen and moderate CO2 are not immediately lethal. The problem is concentration. Even a few percent CO2 at several bars of pressure would be toxic for us without scrubbers, and the high density would make each breath a workout. Another scenario is a CO2 heavy envelope, more like a tempered Venus. Under the dim red dwarf light, thick CO2 could trap enough heat to maintain a wide Goldilocks zone on the day side. It should be noted that in such an atmosphere, a human without protection would black out quickly from CO2 poisoning, long before pressure itself crushed anything. Flames would behave strangely, starved of oxygen, flickering low and sluggish. And then there is the Hycean possibility, a hydrogen-rich atmosphere above a deep global ocean. Hydrogen is not toxic, but at high pressures, it is profoundly unbreathable for us and dramatically changes how heat moves. Optimistically speaking, this could create a stable, mild climate over the ocean eye, with temperatures near the freezing point of water, yet comfortable for extremophile life. For humans, though, the mix would be both asphyxiating and, with any added oxygen, potentially flammable. So it's time to find out the truth about human survivability here. Even in the best-case nitrogen scenario, we would almost certainly need pressure suits and closed-cycle breathing gear. The good news is that models suggest temperatures and radiation levels on the day side could sit within ranges our technology can handle. This is not a sterilizing inferno. It is a heavy, alien blanket of air. Under that blanket, weather would feel slow but powerful. Higher gravity pulls clouds lower and keeps storms more compact. But greater pressure means raindrops fall faster and hit harder. Thunder would sound muffled, as if heard through a wall, because dense air damps sharp noises. Winds might look gentle from a distance, yet their momentum in that thick atmosphere would shove against you like a steady ocean current. Walking outside, you would see towering cloud decks glowing in deep red twilight, curtains of rain sweeping across the ocean eye, and perhaps perpetual mist, where warm sea meets cold night. For us, this is not a shirt-sleeve world. But for any native life that has evolved under those conditions for billions of years, that crushing, dim, red-lit atmosphere could feel as effortless and normal as our own blue sky does to us. And in the next section, we will ask how such organisms might reshape that air in ways we can detect across the void. Photosynthesis in red light, alien plants, and pigments. If the air of LHS 1140b is thick and red, what colors would its living worlds choose? In the hunt for alien life, that simple question hides a deep truth. Biology has to bargain with the light its star is willing to give. It should be noted that LHS 1140 is a cool red dwarf. Most of its energy pours out as deep red and infrared, with only a thin trickle of blue and almost no harsh ultraviolet. This means the color palette available for photosynthesis on this planet is shifted compared with Earth. Our blue-white sun floods our biosphere with visible light across the spectrum. So terrestrial plants evolved chlorophyll tuned to those wavelengths, reflecting green and absorbing mostly red and blue. But while that works beautifully here, it is a poor deal under a dim crimson star. On LHS 1140b, any photosynthetic organism that wastes photons loses the game. So it's time to find out the truth. Alien analogs to our plants might not be green at all. They could evolve pigments that reach far into the red and infrared, grabbing every low-energy photon they can. To our eyes, if we could see them, they might look extremely dark, deep maroon, purple, or almost perfectly black. On Earth, we already see hints of this strategy. Some cyanobacteria use special pigments to harvest far red light in shaded ponds. Now imagine scaling that trick up to a whole planet under a red dwarf. Optimistically speaking, you might get layered photosynthetic carpets, with one pigment system on top absorbing the brightest red, and other pigments below tuned to slightly different infrared bands, each layer stealing what the one above misses. Energy is scarce, so nothing goes to waste. However, there is a trade-off. Infrared photons carry less energy than visible ones. Microbes that specialize in these wavelengths might be incredibly efficient, but grow very slowly, turning the surface into a world of patient, dark biofilms, rather than fast-growing jungles. Along the Goldilocks zone terminator, where the light is permanent but gentle, we might see low, dark mats hugging wet ground, or forests of thick, purple-black fronds, their surfaces dull and light-drinking by day. Perhaps bioluminescent, with faint reds or blues by night under the unmoving star. So let's begin to think like observers again. Would such alien pigments leave a planetary fingerprint we could detect from 48 light-years away? On Earth, vegetation creates a sharp red edge in reflected light, a sudden jump in brightness from red to near infrared. On LHS 1140b, the edge might be shifted deeper into the infrared as pigments adapt to the star's spectrum. If a whole hemisphere is coated in these dark photosynthesizers, the combined signal could, in principle, imprint itself on the planet's light curve. Could JWST, or the next generation of giant telescopes, actually see that shifted red edge on this distant world? Or would an alien biosphere remain perfectly camouflaged against its crimson sky? In the next section, we will push beyond pigments and ask whether those same organisms might transform the entire atmosphere into a beacon of chemistry we cannot ignore. Microbes in the deep, life in a global ocean. If pigments can hide in the glare of a crimson sky, what about the worlds they build beneath the waves? Because if LHS 1140b is a true Hycean planet, then the real story of this distant world may unfold not on land, but in a vast global ocean. So let's begin with that ocean itself. Picture the substellar point, where the red dwarf star hangs motionless in the sky. Directly beneath it, the upper few hundred meters of water form a dim, red-lit sea, the only place where starlight is strong enough to matter. But while this layer glows in deep scarlet, the light fades quickly with depth. Within a few kilometers, day collapses into permanent night, and under the planet's stronger gravity, pressure mounts far faster than it does on Earth. In the hunt for alien life, that glowing skin of water is prime real estate. Here, photosynthetic microbes would harvest the red and near-infrared light of the star, tuning their pigments to the spectrum we saw when we talked about the shifted red edge. Thin as it is, that energy could still power a basic food web, microbial mats drifting near the substellar point, filamentous colonies clinging to floating ice at the edge of the Goldilocks zone on the surface, and tiny grazers, simple multicellular organisms, filtering the water for cells like living dust. But what happens once we drop below the last red photons? In the deep ocean, photosynthesis fails, yet chemistry takes over. It should be noted that a super-Earth with a thick ocean and active interior is a perfect engine for hydrothermal systems. Along ridges in the crust, black smoker-like vents could gush hot, mineral-rich water into the abyss. Around them, chemoautotrophic microbes would thrive, using gradients in hydrogen, methane, or sulfur to build organic matter in total darkness. This means entire ecosystems could bloom far from starlight. Tube worm analogues, gelatinous filter feeders, or mats of simple multicellular fronds might cluster around vent fields, feeding on the chemical factories of the microbes. Optimistically speaking, LHS 1140b's higher gravity and deep ocean could support more vent sites than Earth, multiplying the number of oases on this otherwise lightless seafloor. And because the planet is tidally locked, circulation becomes crucial. Warm water near the substellar point would rise, flow outward, cool, and sink toward the night side, dragging nutrients and organisms with it. Imagine a slow, planet-wide conveyor belt carrying photosynthetic cells into darkness where they die and decompose, then returning mineral-rich water back toward the light. Could this global loop knit the day and night hemispheres into a single, continuous biosphere? So it's time to find out the truth about our expectations. Even if LHS 1140b never grows forests, continents, or animals walking on solid ground, a deep, world-spanning ocean filled with microbial and simple multicellular life would still be staggering. For the first time in human history, we would know that a distant, Earth-like planet has turned starlight and stone into a living ocean, and that the universe may be far less lonely than it appears. Could complex life evolve under a perpetual red twilight? But could that living ocean ever go beyond microbes? If we zoom in on LHS 1140b's dim red coastline of light, can we honestly imagine forests of alien biology, or even minds looking back at the star that warms them? To answer that, we have to confront the hard limits first. This planet is a super-Earth, with gravity likely close to twice that of Earth's. This means tall, spindly creatures are strongly disfavored. Weight is expensive. Add in the possibility of very little or no land, and there may be no equivalent of continents where complex terrestrial ecosystems can diversify. The red dwarf star delivers only a muted, reddish glow, so photosynthesis has less energy to work with. And because the world is probably tidally locked, the dayside-nightside contrast is extreme, with only the Terminator band offering long-term stability. In the hunt for alien life, those constraints sound brutal. High gravity compresses atmospheres and bodies. Limited light narrows the energy budget. A narrow Goldilocks zone on the surface may fragment habitats and slow evolutionary innovation. Would that be enough to choke off complexity before it really gets started? But while the challenges are real, the advantages are profound. Red dwarf stars like LHS 1140 can shine for trillions of years. It should be noted that this gives evolution a timescale utterly beyond anything Earth has enjoyed. If a thick atmosphere and deep ocean smooth out temperature extremes, the twilight ring could maintain stable climates for billions of those years, with currents and winds gently redistributing heat. Oceans are remarkable buffers. They soak up shocks from stellar variability and volcanic outbursts, giving fragile ecosystems time to adapt rather than collapse. So let's begin to picture what complex life might actually look like there. Under high gravity, we might expect squat, muscular organisms hugging the seafloor, built low and wide rather than tall. In dense air or mist near the surface, gliding life forms could spread membrane-like wings and surf slow, steady winds along the Terminator. In the water, broad-finned swimmers could cruise through the red-lit ocean, their skeletons thick and compact. Eyes might be huge and tuned to deep red and near infrared, turning the star's faint glow into richly detailed vision, where we would see almost nothing. Pattern interrupt. Who said complex life must walk on land at all? On LHS 1140b, the ocean itself could be the main stage. Forests might be vertical thickets of flexible, buoyant kelp anchored in the shallows of the eyeball ocean. harvesting infrared light with dark, almost black pigments. Filter-feeding creatures could drift through these alien groves, while agile predators use pressure waves and thermal gradients as much as sight. Could such a world ever host technology, though? That is a much harder question. If there is little or no dry land, the path to fire, metallurgy, and electronics becomes far less obvious. Even if patches of solid ground exist along the Terminator, the perpetual red twilight might slow the development of astronomy. With no moving sun or stars that clearly rise and set, how long would it take an intelligent species to realize it lives on a planet in orbit around a star? So it's time to find out the truth. Does constant, predictable twilight help or hinder civilization? On one hand, unchanging conditions could be a huge advantage. Agriculture along the temperate ring would not suffer from seasons or harsh winters, and settlements might stretch in a continuous band around the planet. With no nights of deep cold, infrastructure could last longer, and weather might be more manageable. Optimistically speaking, that kind of stability could give any intelligent ocean dwellers or shoreline tool users a very long runway to develop complex societies. On the other hand, the very same stability might reduce the evolutionary and cultural pressures that drove rapid innovation on Earth. There may be fewer environmental crises to force technological leaps. Without clear views of the wider universe, curiosity about the cosmos might bloom more slowly. And if most intelligence is aquatic, building radio telescopes or spacecraft from the bottom of a global ocean becomes an immense engineering challenge. So where does that leave us? Cautiously balanced between promise and doubt? Microbial life and simple multicellular organisms in a buffered twilight ocean seem well within reach of known physics and chemistry. Layered mats on the seafloor, drifting planktonic webs, and even complex food chains of swimmers and grazers all feel plausible. Truly Earth-like complexity, large land animals, rapid technological civilizations, visible cities, is much harder to guarantee. But while we cannot assume LHS 1140b is teeming with thinkers, we also cannot rule out that given unimaginable time under a gentle red sun, evolution might find its own, very different path to complexity. And if it does, how would we ever notice from 48 light years away? In the next section, we will turn from imagination back to data and ask what our telescopes could actually see if LHS 1140b's twilight ocean is, in fact, alive. Sniffing for life, oxygen, methane, and other alien clues. So if there really is something alive in that twilight ocean, what trace would it leave in the air above? In the hunt for alien life, we rarely see the organisms themselves. Instead, we look for the fingerprints they stamp onto a planet's atmosphere. Astrobiologists call these fingerprints biosignatures. They are not just single gases, but combinations of gases that should not happily coexist for long without something constantly stirring the chemical pot. Oxygen, methane, and carbon dioxide are the classic trio. On Earth, plants and microbes keep oxygen levels high, while other microbes release methane. Left alone, these two would rapidly react away. Their long-term partnership in our own atmosphere is a sign that something is relentlessly pushing the system out of balance. But while oxygen is often treated as the headline act, it should be noted that oxygen alone is not a smoking gun. Ultraviolet light from a red dwarf star can split water vapor, letting lightweight hydrogen escape to space and leaving oxygen behind. Certain mineral reactions can also stockpile oxygen without any biology at all. This means a world like LHS 1140b could, in principle, build up an oxygen-rich sky, even if its global ocean were utterly sterile. The real prize would be oxygen plus a reducing gas like methane or other mixtures that scream chemical disequilibrium. Imagine we saw strong oxygen, a clear methane signature, and a background of CO2 all at once on a habitable, ocean-bearing super-Earth. How would we explain that without life constantly replenishing at least one of those gases? Optimistically speaking, we would struggle. So how could we test LHS 1140b's air from 48 light-years away? When the planet passes in front of its star, a tiny fraction of starlight filters through the atmosphere. JWST can spread that light into a spectrum and look for the telltale bites taken out at wavelengths where water vapor, CO2, methane, or even ozone absorb. This is transmission spectroscopy. On the night side, or as the planet slips behind the star, we can also study its own faint thermal glow, searching for the same molecules in emission. Future extremely large telescopes on Earth, with mirrors 30 to 40 meters across, will add sharper vision and different wavelength ranges, letting us cross-check any tantalizing signal. However, nature loves to trick us. Volcanic worlds can belch out methane and other gases. Harsh starlight can sculpt strange chemical mixtures in the upper atmosphere. Thick clouds or hazes could hide a thriving biosphere beneath, leading to false negatives, while exotic but lifeless chemistries might mimic biology and give us false positives. So it's time to find out the truth. Not with one detection, but with careful climate and chemistry modeling, checking whether any non-biological scenario can really fit all the data. And if, after all that skepticism, LHS 1140b still shows a strong, persistent biosignature, what then? Would we be staring at proof that life is common in the universe, or at a single, exquisite exception? In the next section, we will face that question head-on. Future Eyes on LHS 1140b. From JWST to giant ground telescopes. So if LHS 1140b really is whispering life across 48 light-years, how do we turn that whisper into something closer to a clear sentence? In the hunt for alien life, this is where the hardware of the next few decades becomes just as important as the planet itself. The story actually continues with JWST. Current and planned programs are not about a single dramatic transit, but about patience. Observing LHS 1140b over and over again. Multiple transits, multiple secondary eclipses, building up a stack of spectra until the noise drops and the signal stands out. Each new visit lets us refine the fingerprints of molecules in the atmosphere, from water vapor and CO2 to methane and maybe more exotic species. This means we are not just asking, is there an atmosphere, but how thick is it, how cloudy is it, and how does it change with time? By comparing the planet's spectrum when it passes in front of the star and when it slips behind it, JWST can begin to separate day-side and night-side temperatures. For a tidally locked world in the Goldilocks zone of a red dwarf, that difference tells us about winds, clouds, and whether a potential ocean is efficiently moving heat around. But space telescopes are only half the story. Over the next decade, the new generation of giant ground-based observatories will come online. The Extremely Large Telescope in Chile, the 30-meter telescope, and the Giant Magellan Telescope. Their mirrors, tens of meters across, will collect far more light from the LHS 1140 system than any current ground-based instrument. Here's the pattern interrupt. We usually think of Earth's atmosphere as the enemy of astronomy. Yet with advanced adaptive optics and high-resolution spectrographs, these telescopes will turn that disadvantage into precision. They should be able to tease apart tiny shifts in wavelength as the planet orbits, separating the star's light from the planet's faint glow. It should be noted that this could reveal finer spectral lines of oxygen, carbon-bearing gases, and even constrain surface pressure by how broad those lines appear. Looking further ahead, proposed space missions such as HabEx and LUVOIR changed the game entirely. Instead of waiting for transits, they would use giant mirrors and star shades to block out the red dwarf's glare and directly image planets like LHS 1140b in reflected light. Imagine not just a single spectrum, but phase curves as the planet orbits, slowly mapping temperature patterns and cloud belts across its surface. Optimistically speaking, each technological step adds a new layer. JWST pins down bulk composition and basic climate. The ELTs sharpen the chemical inventory and pressure. Future direct imaging missions sketch weather, cloud cover, maybe even hints of continents versus ocean. So it's time to find out the truth. Over the next few decades, LHS 1140b could evolve from a mysterious data point into one of the best understood alien worlds in the galaxy, setting the stage for the question we will confront next: what it would actually mean to call such a place alive. What if we actually found life here? So what happens if all that careful observing suddenly pays off? What if, one day, a telescope does not just hint at habitability on LHS 1140b, but at actual life? In the hunt for alien life, the most realistic first contact is not a radio message or a spaceship. It is a spectrum. Imagine JWST's successor, a huge, cooled space telescope, staring at this planet during transit after transit. The light from the red dwarf filters through the atmosphere, and the data come back with a pattern that should not exist on a dead world. We see oxygen, but not just a trace. We see methane, but constantly replenished. Both gases together in the same stable atmosphere at temperatures where liquid water is likely. Every non-biological explanation we throw at it fails. No exotic volcano model, no weird photochemistry. This means the simplest answer is also the most dramatic. Some kind of metabolism is reshaping the air of a distant super-Earth. Scientifically, that single result would be seismic. Until now, we have one data point for life, Earth. Suddenly, we would have two, around a very different star, in a very different planetary system. It should be noted that LHS 1140b is larger, heavier, probably tidally locked, and bathed in red light, yet life still found a way. Overnight, estimates for how common life is in the universe would skyrocket. If life can arise on an eyeball world under a dim red dwarf, where else might it be thriving? But while the equations would change, something deeper would shift too. How would it feel to know that under a red sun, 48 light years away, chemistry woke up? Would we still see Earth as uniquely chosen, or as one chapter in a much longer cosmic story? Religions, philosophies, even everyday conversations about our future would have to grapple with a universe that is not just habitable in theory, but inhabited in fact. Optimistically speaking, LHS 1140b would instantly move to the top of every mission priority list. We would design new, direct imaging telescopes specifically to separate the planet's faint glow from its star, to map clouds and climate, maybe even detect seasonal changes in its atmosphere. Engineers would seriously debate interstellar probes, slow fusion ships, laser sailcraft, or tiny robotic swarms, all racing toward a world we can only see as a pale red crescent. And then the ethical questions begin. Do we have the right to touch that biosphere at all? Even sending microbes by accident on a probe could rewrite an alien ecosystem that has never seen Earth-like chemistry. Do we try to send a message, knowing any reply would take nearly a century? Or do we simply watch as quiet witnesses while another planet lives out its own story? So let's begin an uncomfortable thought. If we find life thriving on a world so unlike Earth, does that make our home feel ordinary or more precious? Perhaps the real discovery would not just be that the galaxy is alive, but that our own planet is one rare expression of something vast, ancient, and only just starting to reveal itself. So it's time to find out the truth. If LHS 1140b is alive, what kind of life could possibly endure a sky that never moves and a sun that never sets? That is where we go next. From TRAPPIST-1 to LHS 1140b, how our habitable world checklist is changing. So if LHS 1140b might host life under a never-setting red sun, how did it beat out our previous favorite, TRAPPIST-1? In the hunt for alien life, that shift is not just about a new planet. It is about how our entire checklist for habitability is changing. For years, TRAPPIST-1 was the poster child. One tiny red dwarf star, about 40 light years away, with 7 Earth-sized planets, all lined up and transiting like clockwork. Several of them sit in the Goldilocks zone, and because they regularly cross the face of the star, we can study their atmospheres with exquisite precision. It felt like the universe had handed us a compact, laboratory-grade solar system. But while the headlines called it a 7-Earth system, the data slowly told a more complicated story. JWST thermal measurements of TRAPPIST-1b and 1c showed they are almost certainly bare rocks with no thick atmosphere to soften their dayside heat. TRAPPIST-1d did not reveal obvious water or carbon dioxide. The outer worlds, like 1f and 1g, now look more like steam worlds or ice balls than temperate Earth-like havens. It should be noted that none of this makes TRAPPIST-1 boring. Instead, it exposed a harsh reality. Even around a relatively quiet red dwarf, intense radiation and stellar flares can strip atmospheres or bake them into uninhabitable extremes. This means simply being Earth-sized in the right orbit is not enough. We have to ask what the star has done to its planets over billions of years. And that is where LHS 1140b steps into the spotlight. Its red dwarf star is also small and cool, but appears even quieter, with fewer violent outbursts. The planet is larger than Earth, roughly 1.7 times the radius, so its gravity can better hold on to a thick atmosphere. Because it transits a nearby dim star, the signal we get when starlight filters through that atmosphere is stronger, making it a dream target for JWST. Early observations suggest that LHS 1140b is dense enough to be mostly rock, but perhaps with a deep reservoir of water and a substantial blanket of gas. Optimistically speaking, we might be looking at a world with a global ocean and a stable, temperate eyeball region facing the star, rather than a fragile, easily stripped Earth twin. So let's begin to see the bigger trend. Our best candidates are no longer just pale blue dots. They are Hycean worlds with hydrogen-rich skies, tidally locked planets with permanent day and night, and strange climates where life could adapt to conditions we never experience on Earth. LHS 1140b embodies this new frontier. It does not look like Earth, and yet it may be far better suited to revealing whether life is common in the universe. But if this is our new gold standard, what exactly should we look for in its atmosphere? And what would count as proof that something is alive there? So, what would life actually be like on LHS 1140b? So it's time to find out the truth. If we had to pick one leading scenario from all the data, what does LHS 1140b most likely look like as a living world? The best fit right now is a heavy, water-rich super-Earth with a thick, non-hydrogen atmosphere and an enormous ocean wrapped around a tidally locked planet. Think eyeball Earth in the Goldilocks zone of a quiet red dwarf, a dark, frozen far side, a brighter, ice-free patch facing the star, and a wide ring of twilight in between where conditions could be truly habitable. So let's begin at the place we would actually choose to stand, the Terminator. Here the red dwarf star never rises and never sets. It hangs over one horizon like a dim, swollen ember, locked in place. The sky is in permanent red-blue twilight, bright enough to see by, never harsh, filtered through dense, moist air that feels heavier than Earth's with every breath. A day on this planet is not the cycle of sunrise and sunset. It is the slow breathing of the atmosphere itself. High, copper-colored clouds drift in stately procession from the hot, substellar ocean toward the night side, carrying heat with them. Weather systems crawl instead of race. Temperatures barely budge from 1 hour to the next, hovering in a mild, almost temperate range. It should be noted that this stability may be one of the greatest gifts a tidally locked world can offer to life. What would that life look like? In the hunt for alien life, this twilight ring is prime real estate. Along the coastlines of the global ocean, dark, almost black, photosynthetic mats cling to rock and ice, tuned not to yellow sunlight, but to deep red and near infrared. Further offshore, the upper ocean glows with slow biological traffic, simple plankton-like organisms floating in the dim beam from the star, and pale, frond-like multicellular forms anchored to submerged ridges. Dive deeper, and light fades completely. Here, chemoautotrophs feed on chemical gradients from the interior, much like bacteria around Earth's hydrothermal vents. On the night side seafloor, under a lid of ice, entire ecosystems might live without ever seeing their star, powered only by planet heat and chemistry. But where would we fit into this system? Human explorers would likely live in pressurized habitats strung along the twilight coast, linked by suborbital craft and submersible tunnels. The bright day side, though hostile at the surface, would be an energy goldmine. Towers and orbital mirrors harvesting the constant glare for power, beaming it back across the terminator. Floating cities could ride the calmer belts of the global ocean, drifting slowly around the planet as currents and winds dictate. Look up and one thing would feel deeply uncanny. The constellations never change. The star never moves. The entire universe appears frozen, while the real motion happens in the water and air around you. Optimistically speaking, this picture is not pure fantasy. It is a blend of hard measurements, mass, radius, orbit, atmosphere hints, with informed imagination about climate and chemistry. This means that if JWST or future telescopes ever see convincing biosignatures on LHS 1140b, this is the kind of world we might be meeting across 48 light-years. A quiet, red twilight ocean, alive in ways both familiar and utterly alien. And if that happens, what exactly would we look for in its spectrum to separate geology from biology? What LHS 1140b teaches us about our own world. And if that happens, what exactly would we look for in its spectrum to separate geology from biology? To answer that, we have to step back and ask a bigger question. What has LHS 1140b already taught us about worlds that are not our own? In the hunt for alien life, this single planet is quietly rewriting several of our assumptions. First, it shows that small, cool, red dwarf stars are not automatic deal breakers. For years, we worried that flares and harsh radiation would strip any atmosphere clean. But LHS 1140's relative calm and the evidence that its planet may still hold on to a thick atmosphere suggest that red dwarfs can host genuinely promising habitable worlds. This means the most common type of star in the galaxy might also be the most important for life. Second, tidal locking turns out to be more subtle than a simple death sentence. Yes, one side of LHS 1140b may face the star forever, while the other lies in endless night. But climate models tell us that with the right atmosphere, heat can flow, winds can blow, and an eyeball ocean under a red sun can remain stable for billions of years. A planet does not have to spin like Earth to be Earth-like in habitability. It should be noted that LHS 1140b is a super-Earth. with higher gravity and likely deeper oceans than we are used to. Yet, instead of ruling it out, that extra mass may actually help it keep its air and water for longer. Optimistically speaking, super-Earths like this might be the prime real estate for life across the universe, even if no such world exists in our own solar system. But imagining that quiet, tidally locked ocean also throws Earth into sharp relief. We live under a yellow star that rises and sets. Our blue sky, drifting clouds, patchwork continents, and moving weather fronts are not universal defaults. They are one particular solution to the habitability problem. What would it feel like to grow up under a fixed red sun, with permanent twilight instead of sunsets, and no true night on the day side at all? Studying a world this extreme, yet still plausibly habitable, forces us to loosen our grip on a narrow, Earth-only definition of comfortable. If life can adapt to a dim red spectrum, a one-sided climate, and crushing gravity, what else have we overlooked? And here's where the humility comes in. From 48 light-years away, we are inferring oceans, clouds, and maybe ecosystems from tiny dips in starlight and faint colors in a spectrum. We are sketching alien weather systems from a handful of photons. So it's time to find out the truth. If we can do this for LHS 1140b, how many other strange living worlds might already be hiding in our data, waiting for us to notice? In the next section, we will follow that question forward toward the telescopes, missions, and discoveries that could finally turn these sketches into a confirmed second cradle of life. Your move under the red sun, where we look next. So let's begin where this whole journey actually started, a tiny dip in starlight. From that faint blink, we followed LHS 1140b from a line in a catalog to a fully imagined world, a heavy super-Earth circling a dim red dwarf, wrapped in a slow, deep orbit inside the Goldilocks zone. We traced the possibilities from a puffy mini-Neptune with a thick hydrogen shroud, to a dense rocky planet, to a global ocean world with an eyeball of open water staring back at its star. Along the way, we walked under red skies that never quite brightened to blue. We stood at the edge of a permanent dawn, where ice may give way to liquid seas. We asked how an atmosphere might move heat from the day side to the night, and whether, in the hunt for alien life, simple microbes could cling to the dim twilight of this distant system. All of it grounded in real data, models, and the hard limits of physics. But while our picture is richer than when that first transit was seen, the core mystery remains. Is LHS 1140b a stripped-down mini-Neptune hiding a deep, high-pressure ocean beneath alien clouds? Or is it a true, water-rich super-Earth with a stable atmosphere and a surface where liquid water can last for billions of years? This means we are balanced between two stories, a beautiful but sterile rock and a living planet quietly evolving under a red sun. It should be noted that the next observations could finally tip the scales. More spectra from JWST, sharper views from the extremely large telescope, and, later, missions built to read exoplanet atmospheres directly may tell us if there is water vapor, carbon dioxide, or even a strange mix of gases out of chemical balance. Optimistically speaking, that imbalance might be the first distant whisper of life. So where do we come in? We can follow every new release of LHS 1140b data, track JWST and ELT results, and support missions that focus on habitable, Earth-like worlds around red dwarf stars. We can keep questioning what life-friendly really means. Does it require a twin of our own planet, or just stable chemistry, liquid water, and time? And here is the harder question. If we could only study one potentially habitable world in real depth over the next few decades, would you choose LHS 1140b, or would you spend those precious photons on another target entirely? Tell us in the comments which version of LHS 1140b you find most compelling. Icy shell with a hidden ocean, stormy eyeball world, or quiet, cloud-wrapped cradle of life. Then subscribe so you do not miss the next steps in this story, and watch our other explorations of nearby candidate worlds. Because LHS 1140b is just one world, the real cliffhanger is this: which of these distant planets will be the first to look back at us through its chemistry and force us to admit we are no longer alone in the universe?